5:30 over in Veal. And that is a bonus opportunity. However, you must bring a sign supporting the faculty team, and your name has to be on the back of the sign.
Are you collecting them?
I will be collecting them after the game. So you don't plan to stay till the end? Is that what you're saying? I'm sorry? Oh, believe me, the faculty will be dead after a very short period of time. I think that it will be done by 6:15 probably. Yeah, it goes quick. So it starts at 5:30. It's in no, it's in Veal.
Okay.
All right, so I'll see you in Veal at 5:30. Oh, of course. Yes, you can put as many names on it as you want. But it's got to be a big sign then. And remember, the signs are going up in my office afterwards. We're having a permanent record of this. All right, there is another opportunity next Thursday, right, at 11:45, exam number 2 on equilibrium calculations. So that will be happening. The SIs, as we said, will be doing some things. I haven't done a problem like this one yet, so I don't think I have. I'm completely losing track of what I've done, but that's okay. What's new, right? I already did sodium cyanide, right? Okay. All right, let's try it this way. What is the pH of a 0.01 molar solution of ammonia? And I'm going to have you assume there's a liter of it. It ends up that for this part of the problem, it doesn't matter how much you've got. We only care about concentration anyway, but I'm going to then throw a twist into it afterwards. We're starting to get you set up for a week from today when we start talking about buffers. All right, so here we've got this solution. I haven't talked a lot about this yet, but let's do this. One of the questions that I always get asked is, how do you know how to write the balanced equation? And there's a simple way to do it. In all of these reactions, we're going to do hydrolysis reactions. In other words, we're going to do a reaction where we react it with water. You don't have to do a hydrolysis reaction for this to work, but for consistency, I prefer to do it this way. And because water can be both an acid or a base, depending on what it's reacting with, you can try to write the equation both ways and see which way makes sense. So what I've written here is ammonia is acting like a base. How do I know it's acting like a base? For a couple reasons. One, the Arrhenius definition of a base is something that when you put it in water, it increases the concentration of hydroxide ions. So we put ammonia into water and we get hydroxide ions. The second definition of acids of bases is the Brunstad-Lowry definition, which says that when you put a base is a proton acceptor. So ammonia accepts a proton from water to make ammonium ion, and in the process it also makes hydroxide ions. The third definition of acids and bases is a Lewis acid and base, and I haven't said anything about acids, we'll get back to that. The Lewis definition, if you think about Lewis structures, are dot pictures. So it has something to do with the electron dot pictures, and if you look at ammonia, this one jumps out at you. Here's ammonia. Here's that lone pair of electrons. A base is a Lewis electron pair donor. And so if you think about what's happening, the hydrogen comes off of the water, attaches onto that lone pair of electrons on the ammonia molecule to make NH4+. Ammonia fits all three definitions of a base. There are some compounds that won't. Some compounds may only be Lewis electron pair acceptors. So for those of you who've already had 113 lab and made it all the way through to the end, you remember coordinate covalent bonds? Oh, I hear the groans. A coordinate covalent bond is a bond where both electrons from the bond come from one of the two participants in the bond. So in this case, ammonia has a coordinate covalent bond with a hydrogen atom. Both the electrons that make up that bond come from the ammonia molecule. Coordinate covalent bonded compounds are all Lewis bases because they donate that pair of electrons. So it's a simple way to see those. But the reason why we have all three of those definitions is to cover everything we've got. Not everything will increase the hydroxide ion concentration when you put it in water. What if ammonia was an acid? If it was an acid, how would it behave? Well, if an Arrhenius base is something that increases hydroxide ion when you put it in water, the opposite of that, the Arrhenius acid, is something that increases H3O+. So if that's the case, then we'd write H3O+ as the product. Well, what do we have to have left then? Oops, I'm hitting the erase button. Don't do that. NH2-. Is there such a thing as NH2-? Yeah, there is. The amide ion. And so could ammonia act like an acid? It could, but it's not one you see very often, so you don't have to worry about that. The other two definitions. The Brunstad-Lowry definition of an acid, let's see, the Brunstad-Lowry definition of a base is a proton acceptor. The Brunstad-Lowry definition of an acid is a proton donor. So in this case, the ammonia donated a proton to the water to make H3O+. The Lewis definition of an acid, if the base is an electron pair donor, the acid is an electron pair acceptor. So if you boil these three things down to, one of them talks about OH- and H3O+, that's Arrhenius. One of them talks about donating protons or accepting protons, that's Brunstad-Lowry. And one of them talks about accepting electrons or donating electrons, that's the Lewis. Those are the three, and you know I'm never going to ask you, is this a Lewis acid or base or a Brunstad-Lowry? But that's why you have those three definitions. So back to this. Which of these two reactions is more likely to be the one that we need? Well, you have a hint staring you in the face in the problem. I gave you a KB. How do you know something's a base dissociation constant or a base equilibrium constant? If OH- is one of the products. So since since you have a KB, you want a reaction where there's OH-, so this is the reaction we want to use. So back to the problem. Ammonia plus water in equilibrium with ammonium ions and hydroxide ions. Initial change, equilibrium. 0.01, we don't care about water. There is none of either of the other two. Okay? The change that occurs comes from the balanced equation, and at equilibrium, we have this. Okay? Now we set up the equilibrium constant expression. Kb equals concentration of the products and the concentration of the reactants. And I gave you the value of Kb in the problem. So now we have to solve for this. Again, I'm going to encourage those of you with quadratic equation solvers in your calculator to use them. If you got it, use it. If you don't have it, have someone help you program your calculator. Or you can make this assumption. Is if I do the algebra on this, 1.8 times 10 to the minus 5 is approximately x squared over 0.01. That's the assumption we made. X is equal to the square root. I've done the math for you already. 0.01 times 1.8 times 10 to the minus 7. For those of you who want to know how to do this, oops, did I do that the right way? 18 times 10, nope, it's times 10 to the minus 8. For those of you who want to know how to do this without a calculator, this is approximately 4 times 10 to the minus 4. Who needs a calculator? It's close enough. So what's the pH? Well, actually, what's X is now 4 times 10 to the minus 4. If we go back up to our table, X is our hydroxide ion concentration. And that's close enough for what we need to do for this purpose. So the POH is equal to the negative log of that. How good are you? What number? What is it? Approximately. What's the first digit? What's the log of 4? What do you think? About 3.5-ish sounds close enough to me. So about 3.5. You can punch the numbers on your calculator if you want a more exact answer. Yes? You ever going to give us, I'm sorry, I still can't hear you. Let me try one like that. It's always good to have someone in the audience to set you up for the next problem. We assumed 1 liter of this. Okay, that would be the pH of that solution. What happens? Oh, you're right, thank you. Sorry. Okay, so that's the POH. The pH equals 14 minus that. How close were we, Jessica? 3.4? So 14 minus 3.4, 10.6. Okay, and it better be basic because we had ammonia, and ammonia is a base. Okay? So now let's go on to the next part of the question that says, what happens to the pH if 0.0, I can't remember what I had, 1.5? 0.1. Let's add 0.005 moles of NH4NO3 are added. Okay. First of all, we have to figure out what the heck NH4NO3 is. We have to go way back to solubility rules. And I said, and I give you a heads up earlier this week. I said we're going to pick on group 1 ions a lot and nitrate ions a lot. Why? What do we know about nitrate ions? They're all soluble. So this is a strong electrolyte. It completely breaks apart into its ions. So I've got ammonium ions and nitrate ions now. Do I care about the nitrate ions? Nope. They're just there as a source of ammonium ions. Why do I care about ammonium ions? Because if I go back up to the equation, where'd it go? Right here. Ammonium ions are going to affect the equilibrium. I already have some ammonium ions in the solution if I dump these in there, so that's going to affect this equilibrium. What else can you tell me about ammonium ions? Are they acidic or basic? They're acidic. They're the conjugate acid to ammonia. So I'm adding acid to this mixture by adding ammonium nitrate. What's going to happen to the pH of this new system? Is it going to go up or down from the number we just calculated? It has to go down. You're adding acid to it. So let's see what happens. Is this what you were wondering about? Okay. Actually, I found a great problem last night that I'll have to share with you in a second. So we approached the problem the same way. The equilibrium reaction is exactly the same. Yes, I'm dumping ammonium ions into this thing, but, Tanya.
I was just going to ask if, like, the OH was, if the balance equation, in the book there was one where the right side, there was like a 2. What happens to X? Do you have to double it?
Yes. Yeah, we'll do diprotic acids on Monday because I want to make sure that I get you the right numbers for a diprotic acid. You going to live over there? Okay. So yes, diprotic acids, if you had a 2 in there, then it would be plus 2x and you'd square it. And remember when we talked about that last chapter, I haven't come up with a good explanation why you both double the x and you square it. But you do. This one, everybody wants to react the ammonium ion with the ammonia. I'll tell you that conjugate acids and bases never react with each other. You will never take a conjugate acid and its base and react them together. It simply doesn't happen. The reason it doesn't happen, an acid always reacts with a base. In this chemical equation, ammonia is a base, hydroxide is a base. Water is behaving like an acid in this reaction, and ammonium ion is an acid. What is the strongest base on that equation? Hydroxide ion. You have a K value for ammonia, 1.8 times 10 to the minus 5, which tells you there's not a whole lot of product made. The strong base, the hydroxide ion, forces this reaction back to the left. What do you think the strong base is going to react with? The strongest acid it can find or the weakest acid it can find? The strongest acid it can find. Ammonium ion is a stronger acid than water is an acid. And so water in this reaction behaves like an acid, but it's going to react with the weak base, not the strong base, because it's the weaker acid up there. So the strong acid always reacts with the strongest base, and the weak acid always reacts with the weakest base. So in the case of ammonia and ammonium ion, one of them is stronger as an acid. Ammonium ion is a stronger acid than ammonia is a base. And so that means that it's going to have to react with the strongest base it can find. How can you tell if it's a strong acid or strong base? If you're given an equilibrium constant, you can look at the value of the equilibrium constant. So in the case of ammonia, Kb is 1.8 times 10 to the minus 5. It's a small number, so therefore it's a weak base. What about something like HNO3? Is HNO3 a strong acid or a weak acid? Somebody said it over there. Why? What do you know about all nitrates? They're soluble. You put a nitrate into water, what happens? It falls apart into its ions. What's the definition of a strong acid? It dissociates 100%. It completely falls apart into its ions. So any soluble compound, chlorides, all chlorides are soluble except silver, mercury, and lead. So HCl is a strong acid. HBr, all bromides are soluble. Chlorides, bromides, and iodides follow the same rule. So HBr and HI are strong acids. H2SO4, sulfuric acid. The first proton is very strong. The second one is debatable. Phosphoric acid, no, it's not. But perchloric acid is. So the strong acids that you need to know One, two, three, four, five, six. I'm missing one. What am I missing? Not HF. Why is HF not a strong acid, by the way? What does HF have that HCl doesn't have? It's very electronegative. HF has hydrogen bonding, but HCl doesn't. It is higher on the table, but HF is a very weak acid, it ends up. So these are the ones that how do you know these are strong? Because you need to memorize them. How do you decide if a base is a strong base? What are the solubility rules for hydroxides? Group 1 compounds and the large ones on the bottom of group 2, barium and strontium. And so all the group 1 hydroxides, sodium hydroxide, lithium hydroxide, potassium hydroxide, are all strong bases because when you put them in water, they fall apart. And strontium hydroxide and barium hydroxide are strong bases. Anything else is weak. So your assumption is it's weak unless you know it's one of those soluble ones. There's a note on my board. I think Amelia wrote it up there. The one about pH? Or was that Susie? Susie wrote that one up there. pH has absolutely nothing to do with acid strength. You can have a weak acid with a low pH. You can have a strong acid with a very high pH. It'll still be less than 7, but it'll be high. pH only tells you how much hydrogen ion is there. Acid strength is how much does it dissociate. If it dissociates 100%, it's a strong acid or base. If it only dissociates a little bit, it's a weak acid or base. And then there's varying degrees of weakness. All right, let's go back to this one, ammonia plus water. As I said, everybody wants to have the ammonium ion react with the NH3 because they say, oh, one's an acid and one's a base. But if you always remember conjugate acid-base pairs will never react with each other, you'll be okay. So if that's the case, we started with 0.01 molar ammonia. We don't care about water. We're starting all over. We're starting from scratch. We added 0.005 moles of ammonium ion. It's in 1 liter, remember? I said assume 1 liter. It makes it easier. The other assumption is that you don't get a change in volume when you mix things, but that's a detail that I'm not going to worry about. And there's none of this. If you think about Le Chatelier's principle, which we talked about briefly, we've already got some product. So that means that if we compare this reaction with the one where there was no product, we're not going to get as much dissociation. Well, that makes sense because we've already said the pH should go down since we're adding an acid. That means we shouldn't make as much hydroxide. So all of this is building together. What's going to happen? How do you decide whether to do a plus or a minus sign here? Because sometimes you'll do a minus sign. How would you decide if this is plus X or minus X? How? It's used up? No?
Which direction the reaction?
Yeah, how do we decide which direction the reaction is going to go? Actually, right now, I'm adding NH4, but I'm going to start from scratch. I'm going to tell you mix 0.005 moles of NH4 with 0.01 moles of NH3. Yeah. It has to do with the Q. You'd calculate Q. All right, without your calculators, because I think you can all do this, what's the value of Q for this reaction? How do you calculate Q? It's the concentration of the products, raised to their stoichiometric coefficient, divided by the concentration of the reactants, raised to their, it's the same as K. So what's the value of Q? 0. Why? Because there's no hydroxide ions. So the value of Q for this reaction is 0. Is 0 greater than or less than K? K is 1.8 times 10 to the minus 5, so Q is less than K. If Q is less than K, which way does the reaction go? To the right. So you could calculate Q and figure out which way the reaction is going to go. For this example, there's an even easier way. How do you know the reaction is going to go to the right? Because there's no product. There has to be some product. We can't have 0 over there. In order to have equilibrium, there has to be some of it there. So this, and we know we have water and ammonia, so we have reactants, but we don't have products, so we have to make some products. But you can always calculate Q to find out what the sign is. The example that I found last night was a reaction where the value of Q was such that you knew it had to go from right to left instead of left to right. That doesn't change how you do the problem. Instead, you just say plus X here and minus X here if that was the case. It's not the case for this reaction. So we're going to lose some ammonia, we're going to get some ammonium ion, and we're going to get some hydroxide ion. And we know that it's that for every one of these that we get, we're going to get one of these and use up one of these. So there's our equilibrium concentrations. Everything else stays the same. So we're going to make our assumption again, except now we're not going to assume X is less than 0.01 because there's a smaller number up there. We're going to assume X is less than, whoops, too many zeros, 5, 0.005. And if we make that assumption, then 1.8 times 10 to the minus 5 equals X, oops, I could leave the X, times 0.005 over 0.01. Doing the algebra, X equals 3.6 times 10 to the minus 5. I think I did that math right. Move the 0.01 to the left, move the 0.005 to the left. 0.01 divided by 0.005 is 2. So I get 3.6 times 10 to the minus 5. And so which equals the hydroxide ion concentration. Got your calculator there, Jessica? That's right, I know you can do the problem. 3.65 10 to the minus 5, negative log. Because I want to get a nicer number this time. 4.44. And so the pH equals, 9.56. Compare that with what we had before. 9.56 here, up here, we had 10.6. So we added some acid to it. We expected the pH to go down. It did indeed go down, and it went down to a nice simple number. Susie? Does the pH go down because the Ka goes down? K is a constant. K doesn't change. The Q changes when you add something. Remember, Q is the value of that expression, this algebraic expression. Where'd it go? Q and K have the same algebraic form, except Q is true at any point in time, but K is only true at equilibrium. How did I know the pH was going to go down? Great question. Sets me up for the next topic. How did I know the pH was going to go down? There's a nice simple one for you. What's the pH of a 0.01 molar solution of HCl? Well, HCl is a strong acid. So you put it into solution, you get H plus and Cl minus. So the concentration of H plus is 0.01, or if you prefer, 1 times 10 to the minus 2. And so the negative log of 1 times 10 to the minus 2 is 2. So the pH of this solution is 2. What is the pH of 0.01 molar NaOH? Sodium hydroxide, all hydroxides are soluble except group 1 compound, so this completely dissociates. We get 0.01 molar hydroxide ion, 1 times 10 to the minus 2. The pOH is 2, and so the pH is 12. All right, here comes the hard one. What is the pH of a mixture of 500 milliliters of 0.01 molar HCl with 500 milliliters of 0.01 molar NaOH? Equal volumes, equal concentrations of a strong acid and a strong base. Anybody want to guess the pH?
7.
How'd you get that? Just guessed? Why'd you guess 7? Because the acid will neutralize the base. A strong acid neutralizes a strong base. Well, what is the acid? Well, it's H plus, and OH minus goes to form water. So the pH of pure water is 7 at 25 degrees C. So yes, the pH equals 7. What about these two? Isn't there some sodium ions and some chloride ions in there? As a matter of fact, if you go way back and you say, oh, look, we have NaCl aqueous. It's a soluble, or excuse me, NaOH aqueous. Getting ahead of myself here. With HCl aqueous to form water plus NaCl aqueous. An acid plus a base equals a salt and water. Uh-oh, not net ionic equations again. Yes, we're going to do net ionic equations yet again. There's the ionic equation for the molecular equation of sodium chloride plus, sodium hydroxide plus HCl. These two are the same on both sides, so the net ionic equation is this one. Okay, remember net ionic equations? Here comes your real challenge question. What is the pH of 0.01 molar sodium chloride? Why?
Because it was 7 5 minutes ago.
Because it was 7 5 minutes. But wait a second. Why would it be 7?
Because it's just salt.
It's just salt.
Yeah.
So a salt is not acidic or basic? Now you have to be very careful. When you say salt to me, I don't think sodium chloride. Salt to me is a cation with an anion. So it's just sodium chloride. It's just table salt.
Yeah.
Okay. If I put sodium chloride into water, what do I get? I get ions. And I still have water, don't I? What's the pH of this stuff over here? 7. What's the pH over here? 7. There's no change. Sodium chloride is a neutral salt, chemical salt. When you take sodium chloride and put it in water, the pH of the water will not change. What about this compound? Ammonium chloride. All ammonium compound, all chlorides are soluble except silver, mercury, and lead. So this is a soluble compound. This is an aqueous compound. And also all ammonium ion compounds are soluble. That was one of the other solubility rules. So when you put this into water, you get this. Oops, learn to write chemical formulas. You get ammonium ions and chloride ions. But what do we know about ammonium ions already? They're acidic. How do we know they're acidic? Because they're the conjugate base, the conjugate acid to ammonia. So ammonium ions plus water give me an acidic solution. There's a very simple rule. Let me write this the other way. The cation or anion that results from a strong base or acid, cations come from bases, anions come from acids, will always be neutral. Why will it be neutral? If I have sodium ions, which come from sodium hydroxide, and I put them into water, and we assume that it behaves like an acid, cations behave like acids, what's it going to do? It's going to make NaH plus OH minus. Let's see. That would be a base, yes. We want to, if it behaves like an acid, it can't behave like an acid, can it? Unless it makes NaH, which has a minus, which would be a hydride ion, plus an OH minus. If it did that, is this a balanced equation? Chemically, is it balanced? Yeah. Electrically, is it balanced? No. So it can't behave, it can't accept a hydrogen from here. It can't, can it increase the hydrogen ion concentration? Can we make H3O plus if we put sodium ions into water? Nope. There's no way to make H3O plus, there's no hydrogen. We can't, there's no electron pairs, so we can't use the Lewis definition. So this would be the equation. Well, is that even possible? No, it doesn't happen. That can't happen. So sodium ions are just going to sit in water. They don't react. Sodium ions will have a pH of 7. Ammonium ions, when you put them in water, though, will react to give you H3O+. Ammonium ions are acidic. If the cation and anion of a strong base/acid are neutral, of a weak base/acid are there's two statements here. I'll read it two different ways. The cation of a weak base is acidic. The anion of a weak acid is basic. So, ammonia is a weak base. When it reacts with water, it makes ammonium ions and hydroxide ions. This cation that resulted from this weak base is an acidic ion. Acetic acid is a weak acid. That anion that results from the weak acid, acetic acid, acetate ion, which is the anion of the weak acid acetic acid, is basic. So, is NaCH3COO acidic, basic, or neutral? Bless you. Is sodium acetate acidic, basic, or neutral? What you've got to do to answer the question is you have to look at both the cation, sodium ion, and the anion, acetate ion, and check both of them. Sodium is the salt, or is the cation that comes from a strong base, so therefore it is a neutral ion. Acetate is the anion that comes from a weak acid, so therefore it's an acidic ion. Did I say that right? No, I didn't. Acetate is the anion that comes from a weak acid, therefore it's a basic ion. So I have a neutral ion and a basic ion. If you mix a neutral with a basic, what do you get? Base. Sodium acetate will give you a basic pH. What about ammonium nitrate? Acidic, basic, or neutral? Ammonium ion comes from ammonia. Ammonia is a weak base, therefore ammonium ion is acidic. Nitrate ion comes from nitric acid. Nitric acid is a strong acid, so therefore nitrate ion is neutral. So I have an acidic ion and a neutral ion, so ammonium nitrate will be acidic. Back to NaCl. Sodium comes from a strong base, NaOH, so it's a neutral ion. Chloride comes from HCl, a strong acid, so it's a neutral ion. So you have two neutral ions. This will be neutral. Now the tough one. Ammonium acetate. Ammonium ion comes from ammonia. Ammonia is a weak base. Therefore, ammonium ion is acidic. Acetate ion comes from acetic acid, which is a weak acid, so therefore acetate ion is basic. So you have an acid and you have a base. The problem is you have a weak acid mixed with a weak base. Strong acid plus strong base will always give you a pH of 7. No ifs, ands, or buts about it. Weak acid plus weak base, you can't tell. You would compare their K values. Very good. So what's the K value for acetate ion and for ammonium ion? Let's figure it out. We know that a NH3 has a Kb equal to 1.8 times 10 to the minus 5. Its conjugate acid is NH4+. And so for conjugate acid-base pairs, Ka times Kb equals Kw, right? So if you solve this, you can find out that the Ka for ammonium ion is 5.6 times 10 to the minus 10. Okay? Everybody all right with that one? If you do the math, you can check my algebra or check my math with your calculator. You'll see that I'm probably right. Acetate ion comes from acetic acid. And this one's easy because you're going to see it right away. Remember I let you in on a little secret about all textbooks? They all use acetic acid and ammonia because the Kb for ammonia and the Ka for acetic acid are exactly the same value. Makes it easier for me to do the calculations. So the Ka for acetic acid is 1.8 times 10 to the minus 5. So if I just look at acetate ions, again, Ka times Kb equals Kw. Except now I want the Kb, so that's just Kw over Ka this time. Well, guess what? The numbers are exactly the same. So ammonium ion has a K value of 5.6 times 10 to the minus 10. Acetate ion has a Kb value of 5.6 times 10 to the minus 10. So I have a weak acid and a weak base. They have the same equilibrium constant. What's the pH of ammonium acetate? 7. What if the K of the acid was larger than the K for the base? You'd have an acidic pH. If the K for the base was greater than the K for the acid, you'd have a basic pH. Ammonium acetate is unique in that it's going to give you a very nice neutral pH. But it's not, it's just because the Ka value and the Kb value for their starting materials are the same. Most of the time that won't be true. And so if I were to give you any salt, and not sodium chloride this time, for example, ammonium carbonate. Do I want to do ammonium carbonate? Sure I do. Yeah, I can do ammonium carbonate. We already know that the Ka for ammonium ion is 5.6 times 10 to the minus 10. The Kb for carbonate, do you have your P-Chem book? Nope. I'm sorry? That'll work. Got that table in there? Thank you. Carbonate, 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 carbonate. Where's the polyprotic? Is that at the end of the chapter? Tanya, what section was that? Do you remember? There it is. Oh, look, urea. We talked about that stuff. Carbonic acid, H2CO3. There it is. 2.1 times 10 to the minus 4. Because I wanted CO3 2 minus. And actually, I found CO3 2 minus in here. I'll show you. The Kb for carbonate ion is 2.1 times 10 to the minus 4. The Ka for ammonium ion is 5.6 times 10 to the minus 10. So is ammonium carbonate acidic, basic, or neutral? Basic. Because this is the larger K value. So ammonium carbonate will give you a basic solution. Now the question was, why did I look up carbonic acid? Anytime the name of the compound is an acid, it's going to behave like an acid, by the way. That's a big giveaway. Carbonic acid will lose a single proton by this reaction, and then bicarbonate ion can also lose a proton to make carbonate ion. And so you can have a Ka 1 and a Ka2 for carbonic acid. Do you mind looking those two up for me? First of all, before we even look them up, we could figure one of them out because we know the Kb for carbonate, so we could go back to the Ka for bicarbonate ion if we wanted to. Which one do you think is going to be greater? Ka1 or Ka2? And why? Just use logic. Will Ka1 be a larger number than Ka, or will Ka2 be a larger number? 1. Why? It's easier to take off the first proton than it is to take off the second proton. The charged particle will hang on to that, just like ionizing a compound. It's easier to take off the first electron than the second. What'd you get? What's in there? Yeah. Negative second? 7. And the second one? It's almost 10,000, it is 10,000 times harder to take off that second one than the first one. It will always be harder to take off the second proton than the first one. Yeah, we'll talk about that one in a second. So, we're going to do polyprotic acids on Monday, and we're going to talk about structure and acid strength. Hopefully I'll see you all in about 2.5 hours.